In computational complexity theory, a probabilistically checkable proof is a type of proof that can be checked by a randomized algorithm using a bounded amount of randomness and reading a bounded number of bits of the proof. The algorithm is then required to accept correct proofs and reject incorrect proofs with very high probability. A standard proof, as used in the verifier-based definition of the complexity class NP, also satisfies these requirements. Since the checking procedure deterministically reads the whole proof, always accepts correct proofs and rejects incorrect proofs. However, what makes them interesting is the existence of probabilistically checkable proofs that can be checked by reading only a few bits of the proof using randomness in an essential way. Probabilistically checkable proofs give rise to many complexity classes depending on the number of queries required and the amount of randomness used. The class Pcp RQ refers to the set of decision problems that have probabilistically checkable proofs that can be verified in polynomial time using at most r random bits and by reading at most q bits of the proof. Unless specified otherwise, correct proofs should always be accepted, and incorrect proofs should be rejected with probability greater than 1/2. The Pcp theorem, a major result in computational complexity theory, states that Pcp equals NP. The complexity class Pcp is the class of decision problems that have probabilistically checkable proofs with completeness 1, soundness alpha less than 1, randomness complexity O and query complexity O. Definition: a probabilistically checkable proof system with completeness C and soundness S over alphabet sigma for a decision problem L, where 0 SC1 is a randomized oracle Turing machine V that, on input X and oracle access to a string pi sigma asterisk, satisfies the following properties. Completeness: if XL then for some pi, V pi accepts with probability at least C. Soundness: if XL then for every pi, V pi accepts with probability at most S. The randomness complexity R of the verifier is the maximum number of random bits that V uses over all X of length N. The query complexity Q of the verifier is the maximum number of queries that V makes to pi over all X of length N. The verifier is said to be non-adaptive if it makes all its queries before it receives any of the answers to previous queries. The complexity class Pcp RQ is the class of all decision problems having probabilistically checkable proof systems over binary alphabet of completeness C and soundness S, where the verifier is non-adaptive, runs in polynomial time, and it has randomness complexity R and query complexity Q. The shorthand notation Pcp RQ is sometimes used for Pcp 1/2 RQ. The complexity class Pcp is defined as Pcp 1/2 00. History and significance. The theory of probabilistically checkable proofs studies the power of probabilistically checkable proof systems under various restrictions of the parameters. It has applications to computational complexity and cryptography. The definition of a probabilistically checkable proof was explicitly introduced by Aurora and Safra in 1992, although their properties were studied earlier. In 1990 Babai, Fortnow, and Lund proved that Pcp poly equals NEXP, providing the first non-trivial equivalence between standard proofs and probabilistically checkable proofs. The Pcp theorem proved in 1992 states that Pcp equals NP. The theory of hardness of approximation requires a detailed understanding of the role of completeness, soundness, alphabet size, and query complexity in probabilistically checkable proofs. Properties. For extreme settings of the parameters, the definition of probabilistically checkable proofs is easily seen to be equivalent to standard complexity classes. For example, we have the following: Pcp 0 equals P, Pcp 0 equals P, Pcp 0 O equals P. Pcp poly 0 equals corp. Pcp 0 poly equals NP. The Pcp theorem and MIP equals NEXP can be characterized as follows. Pcp O equals NP. Pcp poly O equals Pcp poly equals NEXP. It is also known that Pcp R Q NTIME Q plus poly if the verifier is constrained to be non-adaptive. For adaptive verifiers, Pcp R Q NTIME plus Q plus poly. On the other hand, if NP Pcp O, then P equals NP.